Okay, there we go. So what's the last thing? We're going to add friction to our oscillating systems. And I think I'll review a bit just to get us back to where we were. So we're back to talking about motion in one dimension, force as a function of x, velocity and time. And we had the one we've been studying most recently. Up here. The way we had approached this, though, we had actually taken the conservation of energy and ended up solving this equation. And we had another way to write this, minus omega squared x. This is going to be the generic form. And this omega squared was k over m. So anytime you have a differential equation of this form, two time derivatives, negative sign constant in the original quantity, you're going to get that cosine or that trigonometric solution. And more generally, we're going to see in a minute, you're going to get an exponential solution. So our solution to this was cosine or x equals, okay, let's do this right. Let's do this right. So our solution was x of t equals constant cosine omega t plus alpha. And we've done a little bit of investigation of this thing. Okay. Okay, so that's what we've done so far. I'll just write a review here. The next thing we're going to do, because this is the linear differential equation with constant coefficients, right? That's the reason it has this form. The next thing we're going to do is add the frictional force into the mix. So we did this last time. We now said we had the minus kx, that's just Hooke's law. But then we also said we were going to have a frictional force, velocity dependent, that opposes the direction of motion. So the friction, and I'll just put a lowercase f equals f of v equals minus v times. If you look back in your notes, we actually did a little discussion of this in terms of Taylor expanding a frictional force, and this would be the very first non-vanishing term. So for small oscillations, this is the natural type of friction force to include. And when you have this situation, you no longer have energy conservation. Okay? So energy is no longer conserved. Energy is not conserved. And the proof of that is kind of interesting. What we did was we took the energy equal, this is actually well worth the repeat. So the energy equals 1/2 m x dot squared plus 1/2 k x squared. But that's still the energy, it's the kinetic plus the potential energy. The way we show it's not conserved is if we take its time derivative. Right? The time derivative should be equal to 0 for a conserved quantity. In this case, we have the 1/2 m 2x dot x second derivative, chain rule right here, plus 1/2 k 2x x dot, chain rule again, 2's cancel, we can factor out x dot, and what we're left with is m x double dot a star here. We go back to this differential equation. And if we look at it closely, we see mx second derivative plus kx, bring that to the other side, leaves us with negative bx dot. And so we make that replacement, bx dot, and so what we have is dE dt x dot squared. So energy is decreasing, and it decreases in proportion to how fast things moving, how fast the oscillator is moving. So that's kind of a nice thing to be able to do. Can't always do that because we just analyzed the differential equation, didn't even solve it yet. And we found out that energy is decreasing. Now, I think Landau and Lifshitz do this and use this argument to argue that energy has to decrease, therefore B is positive. But I'm going to go with B positive from the outset because it's a friction force that is opposing the direction of motion. Right? Friction that opposes the direction of motion. That's fair and square. I asked you guys before about Landau and Lifshitz. You know Landau and Lifshitz? Book? The physicists? Landau and Lifshitz? I gotta bring him in class. You had a question?
Doesn't friction oppose the direction of motion kind of by definition?
Yeah, that's why I said we could, that's why I said we'd go ahead and assume B being positive right now. But from a totally formalist point of view, if you don't know that, then you use this as a way to determine the sign of B. I'm just saying I've seen that presented in that manner. But so there we have it. That was what we ended with last time. The next thing we have to do is actually solve this differential equation. So we're going to solve that differential equation over there. We're going to write it down in this form. Plus bx dot plus kx equals 0. And the first thing we do is divide by m to get b over m plus k over, so that's k over x equals 0. And the next thing we do is redefine. So let some of these constants here, let b divided by n be equal to 2 gamma, and k divided by m, we already know, is equal to omega. Put a subscript on that right this time. Yeah, omega naught squared. We're going to put a subscript on that. We'll see. So this gives us the form that we're actually going to solve. And you'll see in a moment the 2 just came in for algebraic convenience. Omega naught squared x equals 0. Of course, we already know that if gamma goes to 0, no friction, we're back to the answer we have on the board over there. But what we have to talk about now is the general solution to this class of differential equations, which is an exponential function. Not only that, it's a complex exponential function. So leave that there. Pursue this general solution. Okay, good. So the general solution to this thing and this is for linear differential equations with constant coefficients. So we'll see the same version of this when we're doing matrix equations. But for the moment, we're just gonna say x of t is proportional to e to the lambda t. We're gonna see in a moment that the lambda is actually complex. But when you take this into here, so let x equal a e to the lambda t, both a and lambda can be complex numbers. Generally will be complex numbers. But this form of the ansatz is really nice because you can see whenever you do a time derivative, you just bring down the power of lambda. So you can take this into our equation, two derivatives gives us lambda squared, a e to the lambda t, then we've got plus 2 gamma, and then one derivative gives us lambda a e to the lambda t, and then plus omega naught squared, and no derivatives just gives us the original function, a e to the lambda t. And we can factor out the a e to the lambda t, which is never equal to 0, leaving us lambda squared 2 times gamma times lambda plus omega naught squared a e to the lambda t is 0. So this is never 0. Therefore, the expression in parentheses is 0. We just find the lambda. See, we're looking for the lambda. We just find it by solving the quadratic equation. Good, so here we go. Quadratic solution here, we have lambda equals 1/2 negative 2 gamma plus minus square root of 2 gamma, the quantity squared, minus 4 times 1 times omega naught squared. And now you're going to see why we have that 2 gamma there. We're going to be able to cancel the 2 here, ditto for the 4's inside the square root. So what we end up with is minus gamma plus minus the square root of gamma squared minus omega naught squared. So yeah, that's just some exponential that we, or some expression that we plug in up there and get the solution. But this one we have to look at a little more closely, okay? There are going to be 3 cases. And the first one I mentioned is actually the most important. So the first case here, we have to talk about the relation of these constants. We're going to have gamma squared less than omega naught squared. Okay? In fact, we're going to want it to be much less. For the moment, we just take it less than, and what we now have is the square root of a negative number. Okay? So under these circumstances, we have lambda equals negative gamma plus minus I. Square root of the negative number, we can pull out the square root of negative 1, square root of omega naught squared minus gamma squared. And if we plug this back into here, now x of t is equal to a e to the lambda t, so that's going to be e to the minus gamma t trig functions. We're just working with exponentials, but we know from Euler's formula we're going to have a cosine and sine right here. So, we can just declare victory right here. In fact, before we go on evaluating this, the magnitude of this part right here, what's the magnitude of the thing in red parentheses? Always.
You would get rid of the plus minus, right?
That's right. But it's more about the fact e to the I times a real number. Remember, we pulled out the root square root. This is always magnitude 1. Okay. Magnitude unity. This complex function. So this is always magnitude unity. This is a constant. Right now these things can be complex, but this e to the minus gamma t we should understand very well. Right? The amplitude, whatever a and e do, whatever a and this e to the I do, this thing is just going to be decreasing in time, right? So we already see that we're getting the exponential decay. At least there's an envelope of exponential decay. In fact, this thing here we know is oscillatory. Okay? So we're going to be getting something like that. But we should pursue this a little farther. Right, this is one of those times when all the study you put in complex number just pays off in spades, because this was just easy, right? We just took those trivial derivatives. But there's a little more there. Depending on how you evaluate this thing, you can take either the plus minus, or you can actually just take one of these signs. What about this number a here? This is a complex number. So this solution here we can write like this. So I'm going to next just take plus sign and look at a there. So we end up with x of t equals magnitude of a e to the I, I'll say phi, because that's how you can always express a complex number. It's magnitude times e to the I phi. I'll just remind you guys, that just means that you've got some point in the complex plane, magnitude a angle phi, using Euler's formula. So that was the a there, and then we'll just take the plus sign, e to the plus I root omega naught squared minus gamma squared t. Oop, I lost the, okay. Let's get this right. I lost the e to the minus gamma t. E to the I root omega naught squared minus gamma squared t. Okay. And now we can ask, what's the real part of this? So this is still complex. Now take the real part, and the real part of, do one more step, of x of t equals magnitude a e to the minus gamma t e to the I, I'll bracket this here, omega naught squared minus gamma squared root t plus d. And now we take the real part of this, and we're just going to get the cosine. Remember, e to the I, something, get the cosine. So the final result that we're going to study carefully, we have an amplitude e to the minus gamma t cosine of root omega naught squared minus gamma squared t plus d. And this is reminiscent reminiscent of what we had the other day without the damping. In fact, if gamma goes to 0, e to the 0 is 1, so we're done with that. And if gamma goes to 0, we're back to our original natural frequency, oscillation frequency. So if you want an oscillator that doesn't decay rapidly, you gotta make sure this frictional coefficient is very small. And then that frequency, we could call this omega, and it'll be very close to the undamped frequency. The damping changed the frequency slightly, small damping slightly. So yeah, now you let gamma go to 0 and you're back to the undamped oscillator. Good, so that's an important one. And that was this case here. I think I'll leave all of this up here. Okay, so that was the case when the damping is less than the frequency here. And we want it to be much less as well, typically, okay? What happens if gamma is greater than omega? Like that. And we don't pull out I, and then just look back at this thing. We don't have to rewrite it. Then this expression is real, purely real, has no imaginary part, and is always negative. Then lambda is real and negative. If you take the minus sign, it's clearly always negative. Okay? Whenever you take the plus sign, you're subtracting off, or you're adding something to this negative that is lesser magnitude than gamma itself. So it's clearly always negative. And then what you have is x of t is simply proportional to e to the minus lambda t. Oh, not minus gamma t, but forget that. E to the lambda t. I'm sorry, gamma t. So I would have had to express it in terms of these gammas, but I'm trying to avoid that. So I'm proving that lambda is just real. So it's e to the lambda t goes to 0. It's purely exponentially damped. It no longer has this feature in here. This one, was damped, but it has that oscillatory nature. This one is purely damped. Just goes like this, and it's called the overdamped case. So this is the overdamped. Overdamped oscillation. And this one over here is the underdamped oscillation. Underdamped oscillation. So overdamped and underdamped. That leaves the third case, which is when gamma squared is exactly equal to omega naught squared. Yeah, so this one's no problem, right? This one is the one that's of great physical interest to us and we'll continue to study. But let's go ahead and look at the third case. So 1, 2, already 3 over here. called the aperiodic case. And I'm going to assign this aperiodic case. And this is a really basic calculation, but it's one that you guys can do. It's not just plugging in this thing in there. There's another solution. Let x of t equal f of t e to the minus gamma t. Take this into x double dot plus 2 gamma x dot plus omega naught squared x equals 0. So take that into this differential equation, what we're studying. Soon gamma equals omega naught. Find f of t and the solution x of t. So that's really standard. What you find is a linear time dependence in this function here. This is a aperiodic case. That's a boundary case of sorts because you have to have exactly this value, right? Omega not being exactly equal to gamma. Good. So anyway, is that the first homework we have for next week, or did we have any on
Yeah,
the list?
this
is
was
the first one.
Yep.
Okay. By the way, Monday there's no class, right? Next week.
Yeah.
Monday's a holiday.
Which one?
President's
Day, I
President's Day,
think.
yeah. So nobody comes here, nice place empty.
Yeah.
Yeah. So that's the first one. Let's see if we can add a couple more to the mix. Periodic case, so these damped overdamped oscillations. What we're going to do is start talking about damped and driven oscillations. That's where these damped oscillations really come into play in applications. Old resonance discussion is going to come into play here. So I don't think we have to say that much more about these. This one you'll find a very interesting little calculation just to complete the mix. We're mostly interested in these underdamped oscillations. Those are the ones we're interested in. I could do a slightly better graph of these just to put that in the mix. You guys may have done the damped driven oscillations in Physics 4B lab. Am I right about that?
I think so. It's been a minute.
Right. So there, instead of, well, we'll set this up. There you're using circuit elements, but there's a complete analogy between electrical circuit elements and these mechanical situations. So really the place to study the math, and, practically that we're doing is not by building masses and springs and watching them oscillate around, but actually with electrical circuits that you can dial in. So we'll just do the general form of this. Maybe we can bring the electrical circuits into play later on. So this topic is, and I'm going to approach it systematically here. So we're doing driven oscillations. had before was just a system where you, it could have been a pendulum, you pull it and then you let it swing back and forth and eventually it comes to a stop. Right? Those are the damped oscillations. The driven oscillations are for the same system, but you're actually somehow driving it, vibrating it, you know, coupling it to an external source of force. So with the driven oscillations, and if we include the damping, we then have this differential equation here, x, two derivatives, 2 gamma, we're gonna keep using this formalism, x dot omega naught squared x. Remember, this was the friction, this was the Hooke's law force. They were on the right side of the minus sign, I've got them over here, but we still have to talk about a driving force, f of t over m. Okay, so that's the driven oscillations. This is still just actually coming back to our original discussion. This is now f of x, x dot and t explicitly, right? This is the whole system. We've got the function of x, x dot, and t over m. So what's going to come, well again, if f of t is 0, it's what we got just before. What I'm going to do first is discuss this system without damping. First, this is because we're going to do an interesting mathematical technique that is simpler without the damping. Consider the case where gamma is equal to 0. So now we have two time derivatives equals f of t over m. And we're going to introduce a solution technique that takes us fully into the complex plane. So there's our differential equation. You know, and of course we know without this driving force, it's just an oscillator. So solution using complex numbers, again, complex functions this time. What we're going to do is let this letter C here, Greek letter C, be equal to x dot plus I omega naught x. So this variable here is going to actually contain the velocity and the position. Because we're taking x and x dot to be real, but this is a combination. Excellent. Okay. And if we take the derivative, I omega naught x dot, and if we take the second derivative, oh, actually, second derivative. First derivative already involves the second derivative that we're looking for. So we can get this combination here. C dot minus I omega naught C is equal to x double dot plus I omega naught x dot minus I omega naught x dot plus, well, the I times the minus I gives us I times negative I gives us 1. So we end up with plus omega naught squared x. So this is interesting. Because we have C equals, and this is just the left side of our differential equation, equals f of t over m. So this trick here has turned our second order differential equation into a first order differential equation. And And that's because these linear differential equations just live in the complex numbers, okay? So you see what we did here? We already got one integral for free. Okay? So now we have to solve this equation because, and when we solve it, we will have x dot and x all at once. Okay, so we want to solve this equation here. So all our complex number stuff in math methods just pays off right here. Okay. So yeah, we're going to solve that one. And let's see what comes out. So to solve our equation to start with there, we do something called variation of constants. And what we're going to do is let this function that we're looking for equal to a t e to the I omega naught t. So the idea of the variation of the constant is instead of taking a as a constant, which would be the solution to the undriven oscillator, right? The undriven oscillator would just be constant e to the I omega naught t. The driven oscillator, we have a of t, so now we apply that there, so we have c dot minus I omega naught c equals, I'll write this out here, dA dt e to the I omega naught t plus a of t I omega naught e to the I omega naught t minus I omega naught, and then that c here is a of t e to the I omega naught t once again. And so what happens is these two go away against each other. Equals f of t over n. So now, got time to the punchline. There's our equality that's left over. Okay? I have this equals this, these two canceled, this was equal to f of t over m. So pulling this out, we have dA dt e to the I omega naught t equals f of t over m. So what we've now achieved is we're just going to multiply both sides by e to the minus I omega naught t, and we'll end up with a first order differential equation for a that is immediately solvable. So dA dt is equal to f of t e to the minus I omega naught t. And this one, of course, we can just explicitly directly integrate. Equal to integral, and f of t should divide by outside of the integral and initial condition. Which practically we're always going to choose this to be 0, but it's principally there, so we'll write it down. So now we finally have our solution. We can tag it on the front or the back, doesn't matter. We'll do this here. E to the I omega naught t times 0 to t f of t prime and e to the minus I omega naught t prime et prime. This thing is reminiscent of something we've been doing in math methods. Kind of looking familiar? Anybody? Not exactly, but it's close to looking like the boundaries aren't the same. Looks like the Fourier transform. Right? And that for a reason. That for a reason. So we'll get a limiting case out of this. Oh, I forgot. C is 0 here. Initial condition. Perfect. We've got a minute or two to see what's going on here. So there's one more thing. We have this derivation. We'll go ahead and work with this next time. But there's one more thing. What's the relation of this to what we were looking for? We're looking for x of t. So what about x of t? We have to go back to the definition of this quantity. C is equal to x dot plus I omega naught x. So what you do is you calculate this thing, you locate its imaginary part, and you divide by omega naught. Okay. So x of t is equal to imaginary part, whatever this calculation gives you, divided by omega naught. Because like I said, you're getting both. You're getting the real part is the velocity, the imaginary part divided by omega naught position here. So I should say it's actually possible to do this whole scheme with the gamma as well. It's just more work. This one is much more clear, especially when you're evaluating them. Okay. So what we'll do next week is we'll just start with this and do a couple of examples. There's some nice results that come out of it. And you guys can practice this calculation because this is using a bunch of stuff we're doing in math methods. Okay. Good.